My name is Gabriella Stefan, and 1 and 2 of 2, 4, 6, 7 students were already my students, right, this year. And we will start this seminar just like this. I will tell you the truth, and I will tell you that I was sick this last week, and like I feel I don't have any energy at all. What do I mean? What do I mean like I don't have any energy at all? You need to make a sentence, and you will say that if I'm saying that I don't have any energy at all, it means that I'm not able to, and you can come up. You can talk to your partner and translate what do I mean. I say I don't have any energy at all. What do I mean? What do I mean like I don't have any energy?
You're not going to stand up?
Okay, very good. If you said that I'm not going to stand up, this is great. What kind of teacher am I? What am I teaching?
Sedentary.
What am I teaching? What am I teaching? Physics, right? And in physics we deal with
energy.
And what else? And what else? What else?
Gravity.
Forces. Okay, you said that I won't be able to stand up, right? What is the force on me right now?
Gravity.
And what else?
Chair.
What from the chair on my body? The normal force. Very good. Okay. And this gravity, where is it applied? Where? On my body?
Center of mass.
Center of mass. Very good. You said that because I'm saying that I don't have any energy at all, you said that I won't be able to stand up, right?
Right.
Where is now my center of mass? Right here, right?
Yes.
Yes? If I want to stand up, what will happen with my center of mass?
It would move up and
It will move up, right? So you said that not having energy means that I won't be able to stand up, or in other words, in physics words, means that I won't be able to do what? What happened with this force on me? What did it do from here to here? What is that word in physics? Begins with D. The force did what?
Displaced.
Thank you very much. The force displaced from here to here. And when a force displaces its origin, what does that force do?
work.
Very good. So what is the definition of energy?
The ability to do work.
The ability to do work. Very good. So you helped us to recall what energy is. Anyway, can you please very quickly tell us how can we categorize energy? How many types of energy do we know? You talk to your partner and quickly tell us. Right, so here you are. You can write down a few words. I mean, when you heard us talking about energy, just one. No, it's scrap paper. You just use the paper which, okay. So the part which does not have anything on it, right? So when you heard us classifying energy, what words do come in place? Here you have, okay, good. Okay, you don't have anything to write with? How come you came very prepared? Is this right? Yes, help yourself. Yep. Okay, so how can I categorize energy? How can I categorize? What are the words? How many types of energy have you heard of? Say it.
Elastic, kinetic, gravitational, electric.
Okay.
Solar, mechanical.
Yep. Right.
Potential.
Okay. So here there are two ways to classify them: kinetic and potential. Now, out of all of this which you listed, nuclear, electric, what else did you say?
Solar.
Solar. Can you please talk to your partner and see which one is kinetic, which one is potential? First, you need to talk to your partner and figure out what is that kinetic energy. Is characterizing what kind of objects? Kinetic. Moving objects, very good, okay? Or moving particles, right? Okay, and potential energy, what is another word we use for potential?
Resting.
Stored energy, okay? So can you very quickly classify this? Let me see. I'll ask you, so what do you think chemical is? Is it kinetic or stored?
Stored.
Which one?
Stored.
Stored, very good. What is radiant?
Kinetic.
Kinetic. What is gravitational?
Stored.
What is nuclear?
Stored.
Say it. Nuclear energy. Is it stored or is it kinetic?
Well, it's stored.
It's stored mostly. Very good. Right. And yes. And what about sound?
Kinetic.
It's kinetic. Why do you say so? Why do you say that sound? The vibration of the right of the sound waves. What kind of a wave is sound? I know transverse and longitudinal. How is sound? Longitudinal, very well. Electrical energy, how is it?
Kinetic.
This one is kinetic, very well. Okay. So you have a feel of how should you classify all of these types of energy. Okay, let's see. What do you think? Another way of classifying energy would be, what's the name of this seminar?
Renewable.
Okay, and?
Energy.
So energy can be renewable and non-renewable. Okay. So can you give examples on your piece of paper of renewable and of non-renewable types of energy? I mean, from what kind of sources can I get renewable energy?
The sun.
You write down? You write down sun and what else?
Biomass.
Rain.
So okay. So is this what we talked about so far, right? You said that energy can be potential and kinetic, right? And you said that kinetic represents energy in motion and potential is the stored one. Forms of potential energy, you were able to classify them and you said there are chemical, gravitational, electrical, and elastic. Forms of kinetic energy, you said is the energy of motion, which can be vibrational or rotational, thermal, radiant, sound, and electric, right? This is the classification of potential and kinetic. What is chemical energy? Is the energy which is stored in molecular bonds. You learned about this, right? Nuclear, you've heard about this. Yes? This PowerPoint will be posted on Moodle for you. Gravitational, have you learned about gravitational and kinetic energy? Yes? And beside classifying energy, what else very important do you know about energy? What else very important do you know about energy? Is it any law? Say it, say it.
Like conservation of energy.
What does that say?
That energy can't be created or destroyed. They can only change forms.
Okay. Very good. So what we wanted to talk about right now is is this. You see this? And what we want to show here is, I mean, if I have a ball right here, I want to know, you know, look here. Who wants to come here and show us what happens? Release the ball from here, from here, from here. Katie, please. Katie? Okay. Yep. Okay, Katie. So, do you see the shape of this track? What do you think we want with the ball to do?
I think we want it to go around.
To go around, okay. Let's see. First of all, go ahead. Oh, did it go? Did it go? Nope. Okay. So maybe we can do some calculations, right? What is that which you can measure? What is that which you can measure? I think this is what I want to calculate, right? What is the height from which I want to release the ball in such a way for the ball to be here on the track when it's at the top of the track? Yes? Is it anything which I can measure?
Measure the radius.
Can you, please, quickly?
It's about 15 centimeters.
This is the diameter?
Yes.
15? What is the radius?
7.5.
Write down, please. So, this is what we know, the radius, right? Just a second, Katie. Katie, can you find some markers right there at the bottom of the stage? Can you please give people slates and they will work 2 of them at a slate? Okay, so what we have is this track here, and this is what Katie was able to measure, the radius, and the question is. The question is, what is the height we need to release the ball from in such a way for the ball, here is the ball, I will release the ball from here. What is the height I want to release the ball from in such a way for the ball to still be here at the top of the track, right? So let me see, givens, R is given, I know it, let's consider, what did you say, 7.5 centimeters? Katie?
Yes.
Should I put here 7.5 centimeters?
No.
What?
0.075 meters.
Okay. What should I find out?
The height.
Right. Okay. So, who can do the calculations? Look here, hold on. What's your name, please?
Vincent.
Vincent, I put this one here is the Earth. Mm-hmm. What kind of energy, because we just talked and you are so knowledgeable about the types of energy, what type of energy do I have here?
Yeah, either you have gravitational energy pulling down and the ball in itself has potential energy.
Is the energy pointing down?
Well...
Is it a scalar or is it a vector?
It's a vector. Wait, no, sorry, it's a scalar, sorry.
What is it? Wait, is it? You talk to your partner. Is it the energy a scalar or a vector? Let's see. What do you think? What do you think?
Scalar.
It's a scalar, right? It's the amount of energy you have for me to stand up, as Katie told me in the beginning of the session today, okay? So I have, what did I ask you last?
You asked me what kind of energy is present.
Right, but I thought that you will be a little bit more picky with me. I thought that you will say, I cannot tell you what kind of energy there is here unless I don't define something. What is that? What is that? Say louder.
Velocity.
What do I need to define all the time? The system. What is my system? The ball and the earth. Very good. So if I have the system here, the ball and the earth, right? Let's see. What should I figure out next? What are the
UOFs, if there are any.
If there are any what?
Unbalanced outside forces.
Very good. F external. Okay, what forces are here outside of my system? My system is the ball and the earth.
You have the track. The track.
The track. And the track will do what on the ball?
It'll act on the ball.
What's the name of the force?
It's friction will act.
What? You see, this is the ball, this is how the track it is. You see the ball is touching the track only on the sides of it. So why do you think I chose these materials?
They don't have very much friction.
Exactly. So let's assume that it's frictionless, right? So if the track, you know, we want to consider the friction forces, then what other forces do you have?
You have a normal force.
Just the normal force, right?
Yeah.
How is it?
It is pointing in the direction of the track, like as.
Okay, look here, right here. Yes?
Yes.
How is it?
It's acting this way.
How?
Perpendicular to the direction of motion.
Perpendicular with the track here, right?
Yeah.
Very good. So here will be like this, and what about here at the top?
It's also acting on it.
Yeah, talk to your partner and tell me how should I draw it? To the right, to the left, up, down? How should I draw it here? How should I draw N here?
Down.
Say it?
Straight down.
Straight down, okay. Okay. Like this, right? Okay. And now, what should I do? What is the conservation of energy? What does it say? What should I do on my system? How did you define energy, Katie? You said that if I will have some energy, right, I will be able to do some work, okay? But while doing work, what happens with my energy?
It goes down.
It goes down, right? So based upon the work done on the system, what happens with the energy? There is a, generally speaking, a change in energy. Very good. So work done by the external forces, F external, right, equals the change in energy, right? Okay, so let's see, what is the work done? What is the work done? Can I have a pen still? And, God, I forgot that I can use this. Okay, this, yes. Document camera.
So, yeah.
Yeah, I need to, okay. So this is my drawing, right? And this is what I was able to measure. I know R, and I need to find out what is H, right? Okay, so then let's say that this one here is H. And you said that I know what the system is. And I know what are the external forces, right? Okay, and then you said that the work done by the net forces, external, will be the change in energy, right? What kind of energy did you say the ball has? Because you told me earlier that there is stored and there is kinetic, right? So right here, when I will release it, what kind of energy will it have?
Potential stored.
Potential stored, very good. And will it be moving or not? Very good. I will consider that here is initial and right here is final, right? Okay, so let's see, work done by normal, yes, is the normal times the displacement times the cosine between the two of them, right? How is normal? Like for instance here, you know, because you told me that here it's like this, right? This is normal, yes? So normal is like this. How is displacement? How is the ball moving? Ball is moving like this, right? So here is displacement. What is the cosine between displacement and force?
9.
Very good. What is cosine of 90?
1.
What is cosine of 90?
0.
You decide with your partner. How is it? What is it?
0.
0, right? Equals delta E. What is delta E? Is E final minus E initial, right? What is E final?
Kinetic energy.
Okay, so I will say E initial equals E final. Why was I able to do this? Because I consider that is frictionless, right? Yes? Okay, very well. Initial total energy is made up of what? The two forms you told me.
Kinetic.
Kinetic plus gravitational stored, right? Initial equals kinetic plus gravitational stored final, right? Okay, right here, you said that it starts from rest. Do I have any kinetic?
Nope.
How do you know? What's the formula?
1/2 mv squared.
Very good. And it's 0, right? Plus, you know what my system is? Here is where I consider that h is 0, right? So, do I have any gravitational stored initially here?
Yes.
How much?
mgh.
Very good. Equals kinetic final. Right here. Will I have? Is it moving?
Yes.
Very good. 1/2 mv final squared plus. Do I have any gravitational stored?
Yes.
How much? Is with regard to this.
mg r.
Very good. It's m, g, and then 2r, right? 2r. Yes. Very good. Okay, so you see m is going away, and then I have gh equals 1/2 v final squared plus 2gr, right?
Right.
Yeah, but I mean, do I know g?
Yes.
What is g?
9.81 meters per second.
Very good. Meters per second squared. And what is r? Do I know it?
Yes.
Yes, Katie measured it, right? What is that which I don't know?
V final.
How should I find it?
Setting it.
How should I find it? Look, you have this one here. You have this one here, okay? What kind of motion is this one?
Circular.
Circular, okay? Is anything missing on my drawing?
Acceleration.
How is it acceleration in circular motion?
To go straight to the center of the circle.
Straight to the center, okay? Let me show it here, ACP, right? Very good, so what should I do next? What is my rescue? Whose law? Whose law?
Newton's.
Very good. Newton's what law?
Second.
What does it say?
Force equals mass times acceleration.
What force?
Centripetal.
Which one of the forces?
Normal.
Which, hey, look at me. Which one of the forces? All of them, right? The net force, right? And here you told me that is centripetal, yes? So F net is, let me see, what is my F, my only F? N equals what? M, what is V squared over R, right? Is it right?
Yep.
Is it any other force? Is it any other force? Mg, you forgot about this one here, right? So is N plus Mg, right? What am I looking for?
You're looking for the minimum height?
You said now what minimum height?
Well, minimum height.
Why did you use the word minimum?
Because the minimum height is what it's going to.
I cannot hear Anna.
When it's at the minimum height, then n will be 0 because that's right at that point where, like, the smallest height that you can have it at, so it would go over.
Okay, can I for making it easier, can I set n be 0? And because you said minimum, I will make sure that I will fix it in the end, right? So then I have mg equals mv final squared over r. M with m, what is v final squared is gr, right? Let's go back here. gh equals 1/2 gr plus 2gr. G, h equals, what is r plus half of an r? 5, like this? R? Okay. But I don't want the ball to come down. I want the ball to still be on the track. So how is my height supposed to be?
Greater.
Okay, so h will be greater than 2.5 r. Can you please tell me what is 2.5 times 7.5 centimeters? How much is it? How much is it? Okay, and Katie, you come here with a ruler. Where is the ruler? Yes? Okay, what is that height? So the height is supposed to be greater than what? Greater than what? Anna, what is 2.5 times?
18.75 centimeters.
18 point what?
75.
I don't think that's...
I mean, where do you hear? Okay, but you said more than this, okay? So here is the ball. Let's see if you try from there. More than this, right? Oh, where is the, did you mark that or not?
No.
Do you want to use a marker?
That's okay. Yeah, I do it for like...
Well, hold on a second. Here it is.
Yeah.
Okay. I mean, but how come? How in the world you see you are doing
Friction.
So, is the energy conserved here or not?
Nope.
Why not?
Because there's friction.
And what else? What else? Where else is the energy lost? Sound. Okay. And what else?
Drag. Like air.
Drag and air friction, right? Not only the friction with the track and with the air, right? Very good. Let's see where can you place it in order to still stay on the track. Nope. Go more. Ooh, very good. Okay. So what was the lesson we wanted to learn, to prove from this demo?
Energy is always lost.
Energy is always lost. Very good. And is this a good thing? What are we trying to do in daily life? To do what? Say it more. To maximize what?
We want to minimize the amount.
To minimize the amount of.
Work for the most amount of energy produced.
Okay. And what would be some ways to do this? What would be some ways to minimize the loss?
Try to make it frictionless.
Okay, try to make it frictionless. This was just an example to talk about energy and conservation of energy. But if we go back of types of energy, Let's see, what did you say? Renewable, no, not renewable, non-renewable energy will be. Do you have a list there? There are some napkins if you want to use some napkins to clean your board. Here are, do you have there any? No? Here. Okay. Mm-hmm. Yes. So can you give some examples of non-renewable energy sources?
Coal.
Okay, list it. Coal, what else?
Oil, natural gas.
Very good. What else?
Nuclear.
Say it again.
Nuclear.
Nuclear. Nuclear, you mean? What is the name of the element in the periodic table of the elements? Begins with U. Uranium. Very good. Okay, so you said how many? 4 or 5? Yes. What about renewable sources of energy?
The sun.
The sun. What else?
Biomass.
Biomass. What else?
Water and air.
Okay, hydro. What else? When you said air, you mean?
Wind.
Wind. Okay. Let's see. What do you think about the U.S. Consumption these days? Is it more renewable or is it more non-renewable?
More non-renewable.
What percent?
It's like
How much?
it's like 90%.
Like what? So let's add up all of the non-renewable. So we have let me see, 37 plus 9 plus 21 plus 25. How much is this?
92.
They're 80.
How much?
I think it's 80.
It's a lot, right? What about the renewable? What percent? What you add them up? It's 4.5 plus.
8.
It's less than 10% renewable, right? But it's your responsibility, your generation, to increase this and use more renewable sources of energy to figure it out. What can you do? Okay. So let's see if. We want to talk about nuclear energy. Do you know where in the world nuclear energy is mostly used?
Europe, America.
Where?
Europe and
Okay.
Japan.
And then in America, in the eastern part. Okay, what about the solar, photovoltaic solar resources? Let's think about how it is in America. Do we use where? In what part of America?
Southwest, yeah.
Okay, where?
The desert.
In California? We have more use of it? Yes. Okay. Now, because you talked about non-renewable sources of energy, and because today we need to talk about energy, I mean, how would you be able to compare? Like, for instance, in your house, you have a natural gas furnace, and your neighbor has oil furnace, right? And you have some values of what is the amount of the fuel you and your neighbor are using, but it's different type. One is oil and the other one is natural gas, right? How should you do in order to compare and to see which one saves more money? For this, we have some energy basic units, and here you have, what is this, a BTU?
British thermal unit.
Say it louder. British thermal unit, right? So you have here 1 barrel of crude oil, how many BTUs, and 1 gallon of gasoline, and so on. Can you use this information and solve this first problem here? You just write down what is given, and then I will go to the previous slide for you to use the numbers, okay? So you have a natural gas furnace in your home that used 92,200 cubic feet of natural gas for heating last winter. Your neighbor has an oil furnace that used 648 gallons of heating oil last winter. Which home used more energy for heating? So, I mean, one is in cubic feet and the other one is in gallons. What should I do? Did you write down the numbers? Okay, what should I do?
Convert to BTU.
Say it again?
Convert to BTU.
Okay, so let's see. Who is using more for heating, you or your neighbors? Your neighbor. And come up with a value. Do you have your calculator with you? Okay. Let's see. Do we have an answer? Yes? So the question is, which home used more energy for heating? Your home or your neighbor's home?
The one that used natural gas.
Huh?
The one that used natural gas.
Yeah, but I mean, you...
I don't remember who was the neighbor.
But I thought you wrote down.
I wrote down the numbers. So we
are.
You. Us.
You are using more?
Yes.
Right. Okay, so maybe you will make some decisions in order to use less energy, right? Okay, so then, but in school, what kind of unit for energy did you heard of? Have you heard of? Joules, right, and kilojoules, right? And what other unit, a tolerated unit, not in the international system of units, not in SI, another unit, which is written there on your food. Say louder. Calories, kilocalories, right, okay, very good. And is it, you said that there is a relationship between energy and work, right? And what would be the third quantity we need to talk about? Energy, work, and what else?
Power.
Power, okay. So what is power?
Work done over time.
Say it again?
Work done over time.
Very good. Work done over time. Okay, so work, energy, and power, you know the definitions for this, right? You will have them posted on the Moodle page, right? You are familiar with this. You are familiar when the work is done in the direction of motion, in the same direction, perpendicular, right? When do we need to use what formula and how did we do? We already applied this when we solved this problem, right? Do you recall we said the force times displacement times the cosine between the two of them? I want to ask you if I have let's now move a little bit from the mechanics to thermodynamics. And in thermodynamics, we work with gases and liquids. We call them fluids. And let's say that, so in mechanics, right? What did you say? The formula for work is?
Changing.
Like this, right? And if here is the force and the displacement is just like this, what is the angle? What is cosine of what? How much? 1. So then work will be F times D, right? Imagine now that in thermodynamics, which I know that you didn't ever took a course in thermodynamics, right? Did you? No, okay, thermodynamics. Let's say that, look, I have this cylinder here, and I'm applying this force on it, and here I have some gas in it, and in the same cylinder, because I'm applying the force, you know, I will be here with my piston, right? What happens with my gas? Say it louder. Okay, very good. And did the piston moved or not?
Yes.
Yes? Let's say that it moved just like this with this delta D. Yes? Okay, so, and here is F. So, let me see. The work is the force times the displacement, right? Times the cosine between them. What is cosine of what? Look, this is the force and in this direction, and this is the displacement. What is the angle?
0.
Right? So work will be F times, this delta D. Yes? But what is that which I can measure to this gas here inside? What can I measure to a gas? Because I know the size of my cylinder with a piston. I can measure the pressure. What else? If I know the size.
Volume.
The volume, right? So pressure, volume. What else? What else can I measure?
Temperature.
Temperature. Very good. Okay. So, but what is the definition of pressure? What is that pressure?
Collisions per unit of area.
Collisions per unit of what?
Area of the...
Of area, right? So when you say collision, you mean some interaction force, right? So force per area, right? Okay, so from here I have forces pressure times area, which means that work will be pressure times area times delta D, right? But if, this is delta D and this is the area, here, what is this one here? What is this? I know delta D, and I know the area of the piston. Look, this is, let's see, what is this? Area is measured in what? Let's do a unit check.
Meters squared.
Meters squared, and this, which is a displacement, is in meters. So what would be this?
Meters cubed.
What is that?
Volume.
Say louder.
Volume.
Very good, okay. So it will be P times what? volume or what? Delta volume, right? So this is my formula for work in thermodynamics, right? What did you say are the parameters in thermodynamic I need to all the time think about? What are the, hey, Vincent, what are the parameters? What are the parameters in thermodynamic?
Oh, sorry, pressure, volume, and temperature.
Very good, okay. So I can have different types of processes. And in some processes, I have some parameters which are constant, right? You're familiar with this, right? How can I derive the formula for work in thermodynamics, starting with the formula for work in? Say louder.
Kinematics?
In mechanics, right? Yeah, okay. So here you have a little bit about laws of energy, right? Here you have loop-the-loop in your Moodle presentation. Here a little bit of power, which you said that is the rate of doing work. Very good. Here you have the first law and the second law of thermodynamics, which you can find in chapters 16 and 18 in your third edition of AP Walker textbook. And we might, if you want, we might scan them for you and place them on Moodle. And what I want to, have you ever heard about entropy? What is that?
Free energy.
Free energy, okay, but in only one word, how would you talk about entropy? What is that?
Chaos.
Chaos, disorder, right? Okay, is it any relationship between energy and entropy? What relationship should be?
With every transfer of energy, entropy increases.
Okay, is it ever possible for the entropy to decrease in a system?
If work is
In
done.
a system, yes, but not in the universe. Like you can,
But isn't the universe a system?
yeah, in the system of the universe, entropy is always increasing.
It's always increasing and never decreasing, right? Okay, so these parameters which we were talking about, pressure and volume and temperature, they can vary, right? And here, let's see, if the parameter which is held constant is the temperature, I think you've learned about this in chemistry. Did you? About isothermal and isochoric, right? Oh, so then you don't really need to study our physics textbook. You know already this from chemistry, right? Okay, so have you learned about let's see, for instance, pressure. Pressure defines a state of a system, or does it define a process? So out of these three, pressure, volume, and temperature, write them down on your whiteboard and tell me which one defines a state and which one defines a process. Process meaning changing of the system from one state to another. Which one defines a state? Which one defines a process? Let's see, temperature defines a state or a process?
Process.
Say it louder.
Process.
A process? I mean, saying this, it means that I cannot ever say that right now I have this temperature, right now, in this state of mind. Can I?
Yes, you can.
Yes, okay, so temperature is what kind of a quantity? Is it defining a state or a process?
State.
A state. What about volume?
State.
A state. I can measure the volume in a certain state. What about pressure? Can I measure the pressure right now in a cylinder with a piston? Can I measure it? Yes, okay, so what kind of a quantity is it?
State.
A state, very good. What about work?
Process.
Work is done in a process, very good. Okay, what about energy? Can I say that energy defines a state? Yes? You said that energy can be gained or lost, right? So what kind of quantity is energy? Talk to your partner. Is it a state or a process, energy? Okay, what kind?
A process.
State.
Is it right? Why do you say state?
Because in chemistry we learned that no matter how you get to a certain energy level, it's still the same. I don't like, for example, if you were going to put a boulder at the top of a hill and it would gain potential energy by getting there, it doesn't matter if it took a zigzag route to get to the top of the hill or it was as efficient as possible.
Right, but I mean, my ball here was I able to say that it has a certain energy right here?
Yeah.
Yes. So is it a state or a process?
State.
State. Okay. Okay. So then you are familiar with this, right? So if I have, I want to ask you. What is this? Who wants to hold it? Who wants to hold it? You want to hold it in your palm? In your palm like this? Hold it only here. Only here. Hold it. Oh. What happens? What happens? I mean, and now you hold it here and release it there. Hold it here. Yep. Yeah, like this. And yeah. What happens here? You can pass it for them to experience it, and then they will see. You can. Yes. And then, let's see, you need to hold this. This will start doing work based upon what? Work done will be able to, how can I do work?
Changing the energy.
How can I change the energy?
If the wheel works.
Why, you see, this one is in contact with my palm. So after a while, it will reach what kind of state? How do I call it? Equilibrium.
Okay.
Equilibrium, right? And then this surface will have what temperature?
Your body temperature.
My body temperature, okay. And will it be a difference in temperature between what and what?
The air and your.
You hold it. Right. And it will be a difference in temperature between this bottom side and the upper side, which is at the temperature of the environment here. Did you learn in your chemistry class about an engine which is very efficient? It's an ideal one. Yes? No.
Or in physics, we learned about some ideal engines, I suppose.
In physics, you learned about what?
Different types of engines.
Right. There is one engine which has an ideal gas, and that one will have the best efficiency. But what is that efficiency? What is efficiency?
When it's work in over work out.
Say it louder.
Work in over work out is efficiency.
Right, so you need to kind of compare what you put in and what you are getting out, right? So based upon what you saw in the previous chart with all of the processes, isochoric, isothermal, isobaric, and adiabatic, the ideal engine is called the Carnot engine, which is following the Carnot cycle. And here you have a little bit of computation about the Carnot cycle, which I put it here for you today, and you can anytime ask me questions and I can help you derive it on your own. But for this, you need to do a little bit of reading. So I swear that this worked before coming here. Let's see, let's help it a little tiny bit. Okay.
Maybe your hands aren't warm enough.
This is what we call the Stirling engine. And with a little bit of help, which was only initially, this works based upon the difference in temperature between what and what?
The top and bottom.
The top and the bottom of this, right? Okay, I really wanted to show you this. I really wanted to show you that the Carnot cycle, you see there in a box, I have the final formula for the efficiency of the Carnot cycle. What does it say? I mean, 1, 2, what kind of transformation process is 1, 2? It says up. Isothermal, which means what is kept constant? Iso, meaning the same, thermal. Temperature, very good, okay. 2, 3 is an adiabatic. Do I have any heat coming in my system or not? Look, it says in the box on 2, 3 in the diagram. Up in the diagram. Do you have any heat coming in? On 2, 3, what does it say in the box? Q equals 0, you see, on 2, 3? Very good. On 3, 4, what is the system doing? My system, that gas, let's say, in the cylinder, is touching, as this guy is touching my, right, something, a surface here, is touching what kind of a source? A cold or a hot source? What? You see on 3, 4, what is that? QC, a cold, right? Let's see, what do you expect with a gas to happen when it's touching a cold source? What is the volume doing from 3 to 4?
Decreasing.
What is it doing? You read the diagram for 3 to 4. Decreasing, right. Okay, what is the pressure doing?
Increasing.
It's increasing, right? Okay, so just looking at that cycle from 1 to 2, 2 to 3, 3 to 4, and 4 to 1, you can imagine what happens with a system with that gas in my cylinder with a piston we talked about earlier, right? I'm not sure how familiar you are with this from your chemistry class. I'm not sure how much is new and how much is... Have you learned about Carnot cycle? No. Have you ever calculated efficiency? Yes?
Yeah.
In your chemistry class?
Mechanical engineering.
In chemical engineering, okay, but not all of you. But what is this thing doing here? What is this thing doing here?
Piston.
Is doing what?
Work.
Work. Based upon what? The difference in, I have two reservoirs. What are the two reservoirs? One is named with C and the other one with H.
Hot and cold.
Hot and cold, right? So these were just a few notions about thermodynamics. And if you keep coming at this seminar, you will find out more interesting stuff. I think this is all for today. If you have any questions, if you want, I can meet with you and show you how the derivation goes and answer you any questions. Do you have any questions right now? No? Okay, so then I'll see. We will post this on Moodle, and I need the slates, please.
What is the middle page called?
It is called. What it says? It's saying here.